Alright, so this is lecture 12 on Numpy, linear algebra, and computational cost. Our outline for today is we're going to start talking about some functions to do linear algebra in Numpy. They're pretty simple compared to the stuff we've been doing the last couple days. Hopefully you'll find that great when doing your homework. So I'd also like to talk about some other concepts that are really important in numerical computing. Today's a good day to put them in. We're going to talk a little bit about computational cost, about what different algorithms do to your code, to your computer, how much resources they use. And then we'll talk a little bit about asymptotic behavior and how we think about computational cost for large calculations. Okay? So I'm excited for today's lecture. This is from some pretty cool stuff. So let's just go ahead and dive right in with Numpy linear algebra. Okay? So the last couple of days we've been reviewing some concepts in linear algebra and in programming, and as you might have noticed, it's kind of a pain to code, triply nested loops to solve the Gauss elimination system, and it turns out that you can have some pathological cases where even if you take the Gauss elimination algorithm as it's directly applied, there's some problems with it. You need to do some extra things called pivoting and other things, so if you ever get zeros on the diagonal. And there's ways that that algorithm can break down and not work. And that's really a pain to deal with. And so fortunately, there are packages that do this for us that have coded better algorithms. And as you're going to see for the rest of this class, what we're going to sort of do this motif where we spend a day and learn a little bit about how these algorithms work, at least just to get a flavor. All right, and then we spend a day getting to practice with the built-in functions that already exist or the functions that are in different modules. And that allows us to have some appreciation for how they work, but also be able to solve more complicated systems than just the ones that we can code by hand. And so there's this dynamic in this class. And so we've just sort of done this for the first time where we've learned how they really work and we've reviewed some linear algebra. Okay, and now we're going to learn how to just use the Python functions to solve some more engineering problems that have a little bit more difficulty to them. Okay, so I'm not going to write all that down, but I'm going to say modules and built-in functions. Okay, make our life easier. All right, and that gives a nice happy face. Okay, and so today we're going to talk about two different modules, or maybe one module and a submodule, so I'll just put one arrow, I guess. So we've talked about it in the past, but it's the Numpy, or numerical Python module. All right, and the numerical Python has a submodule, which is linear algebra. So it's called linalg, which is its linear algebra. Okay, submodule. And within both Numpy and the linear algebra submodule, there are a couple really valuable functions that we can use. And we've already been able to use some, and I've used some sort of casually here and there, and so here's the time I'm really going to introduce them. Example functions that maybe we've already seen, but that now will be required to know that are really valuable include the following. So first, we can just do array math. All right, we've talked about some of this in our lecture on arrays, but we can do things like element-wise addition, subtraction, multiplication, okay, and scalar multiplication. So multiplying by just a constant. All right, these are all really valuable things to an array. So you don't need to write a loop to be able to multiply an array by a single number. This is not true in other languages, for instance, C++, unless you're using vectors. So you can just add v plus w, or you can do v times w, all right, and it goes through and does an element-wise addition. And this can be either a vector or a matrix, okay, or even, higher order if you have three-dimensional, a third-order tensor, all right, this sort of thing. Okay, so array math, we've talked about a little bit about that in the past. There's some other things that are really useful. Sums and dot or inner products. okay, are built in. So if you want to take some matrix, or some vector rather, and you just do np.sum, and you put your vector in there, it will just add up all the elements. So previously, think we had to do a sum as follows. We had to say sum v, and then we did a loop, so we said for I in length, or excuse me, range of length of v, right, colon, and then we did sum v plus equals v at I, okay? That is all now replaced by just this, numpy.sum of v, all right? Super valuable to be able to do, okay? That's one thing. Another one is the dot product, so np dot, okay, if I wanted v comma w, right, this will do the dot product. So again, we had this whole system where we wrote loops, and we had to do dot products, and we did sum, and we did a couple of days of that. And before you get too mad at me, all right, we need to get good at loops for other reasons that are important, and being able to do these sums and dot products are easy practice for us to do with loops at the beginning when we're just getting our feet wet. But hopefully you're a lot more comfortable with loops now, and you don't have to write a loop every time, and now you can just go ahead and plop in numpy.sum or numpy.dot. That's one of the great things about this class, is we kind of learn how it works, and then we learn the easy way to do it, and we move on. And hopefully we've had a little bit of understanding of what's going on under the hood here. And we're going to talk a little bit today about computational cost and why it matters that we know a little bit about what's going on under the hood. Okay, so we can do dot product between two vectors like this, okay, for both of them. We can also do numpy dot dot if I had two matrices. So if I had a comma b, where both of these are matrices, okay, or I can do the same thing if I have a matrix and a vector. So if I have a comma v, ooh, the worst v of all time, okay, now this is a matrix, and this one is a vector, right? So you can do sums and dot products. There's a couple other things that are valuable here. There's a transpose. So a transpose is simply to swap the rows and the columns. So if I have 1, 2, 3, 4, okay, if I take the transpose of that, that would be 1, 3, 2, 4. Okay, where I've swapped these two guys, the diagonal stays the same. So how do I do that? If this was matrix A, in Python this is going to be a dot t. In math, you would write a to the t with a little t up in the upper, I guess superscript is the word I'm looking for. Okay, so that's transpose. Transpose super useful to be able to do that, as opposed to having to write a loop to swap those. I think we might have done that as a homework problem, was to swap things in a transpose. The other thing is to do a norm. Okay, this is called a norm. Some students sometimes get a little confused by a norm. Maybe you haven't heard that word before. The norm is basically a way to get a distance in a vector or matrix. So you're trying to get a magnitude of that thing. So the distance formula is what you've encountered almost certainly in the past to try and get a norm of a vector. So what you're doing here is you're taking the sum over all the components and that are squared. Okay, so you'd have something like this, and then you're taking the square root of that whole thing. So that's a 2 norm, and you can do that either in a vector or in a matrix and add up all the elements and do that case. And so again, Numpy defines a nice function for us. This one is not just in the Numpy package, it's in the linear algebra subpackage. So you need to do np.linalg.norm, okay, and then you'd put in v for vector, or if you wanted to do matrix, linalg.norm, and put in capital A, say, if that's your matrix A. All right? So keep an eye out for those if you're taking a linear algebra class, or you will shortly. This should be pretty useful for you if you wanted to check an answer. Okay? So the last thing that I want to cover in this is how to do linear solutions. Okay? So in the past, in the past 2 days, we've been doing Gauss elimination. Right? This has, forward elimination plus back substitution. There's 3 nested loops, right? In the one, and 2 nested loops in the other. Big, relatively big code for us, right? And Numpy just makes it super easy. There's actually 2 ways to do it. So let me highlight the first way. And let me just remind us here, we've got a dot x equals b. This is the standard form you need to be able to write things in, okay? And what you do here is you call x is assigned to np.linalg. So again, in the linear algebra package, solve. Let me just double check, make sure I'm not screwing up. Yep, a comma b. All right, so look at that. It couldn't be simpler. It's as easy almost as taking a norm. All right, you don't have to write Gauss elimination at all, and it does all the error checking for you and everything. Okay, so np.linalg.solve a comma b, and that gives you the x vector. All right, so that's the easiest way. I highly recommend it. Okay, it's also generally the fastest and I'm just going to tell this to you if it doesn't mean anything to you, don't worry about it, but for what's called a dense matrix, okay, that's as opposed to a sparse matrix. A sparse matrix is basically a matrix with a bunch of zeros all over, and the matrix really doesn't have, it's not full of elements. And that usually doesn't happen in like a 5 by 5 system. But in, say, a 1,000 by 1,000 system, you can have a sparse matrix, and you might need a different way to do that. Numpy and SciPy also have algorithms for sparse matrices, but we're not going to talk about it in this class. Kind of a bummer, you know, but anyway. So the other way to do it, right, is if I have ax equals b, I can also take the inverse of both sides of this, right? So I can do a inverse a x equals a inverse b, right? Remember that I need to leave this on the left because matrix multiplication is not commutative. So a inverse a gives me an I at identity matrix dot x, and this is a inverse b here, okay? And identity times x is just x, so this is x is equal to a inverse b, okay? So now, if I wanted to calculate x, one way is to just do the solve with Gauss elimination. Another way is to go ahead and calculate the inverse. And so it turns out there is an inverse function, so np.linalg.inv of a, and that will calculate the inverse directly. Notice that I don't need to call b here because I don't need to know what b is to calculate the a inverse. All right, so this gives me a inverse, but it doesn't solve for x. So if I want x, I have to execute this guy right here. So I have to execute a inverse dot b. So to do that, then I just do np dot a inverse comma b. All right, so this one has 2 steps, okay, and I need to store the a inverse, okay. So it's a little bit slower and takes a little more memory, but okay, easy for multiple b's. Okay, so if I had, if I wanted to solve ax equals b1, ax equals b1, ax equals b2, etc., and I had a bunch of b's, okay, this would be an easy way to go about doing that. Turns out there's another way that's computationally more efficient called LU decomposition, okay, which I'll write the whole word out. Composition, all right, which is not beyond you at all. It still involves Gauss elimination. Okay, actually all these under the hood in Numpy involve Gauss elimination. They're just Gauss elimination with error checking. So you know how these all work, okay? But LU decomposition is actually a slightly faster way than storing the inverse, or more than slightly faster. It's a better way of doing it, but you don't need to worry about that for this class, okay? That's just bonus learning for you, okay? So happy birthday to all you out there. Okay, so that's all I'm going to say about Numpy linear algebra. Quick 15-minute update on Numpy linear algebra. You should be pros at this. Practice a little bit, you'll be good. One thing to say, there is an example video, okay? So go ahead and check that out, where I go through, do all of these out, do some examples in Python, work that out for you, okay? Check it out. All right, let's move on and talk about part 2. Let's talk about computational cost. Okay, what do I mean by computational cost? So if you remember, way back at the beginning of class, we talked about how computers were, consisted of a CPU and memory and input and output, okay, and these different components of a computer. All right, and we want to know, when we run an algorithm, how much are we taxing these resources? Okay, So when we run an algorithm, how many resources are we consuming? Okay, and specifically we want to know about memory and CPU time. Okay, and lest you think that this is silly, because it's not silly at all, it's really important. Let me just give you just a sense of why this is important. Okay, so suppose you want to calculate, the inverse of a matrix, and it's a 10 by 10 system, and that just takes no time on your computer. And then you do one that's a 100 by 100 system, and it takes a little longer. And you do the one that's 1,000 by 1,000, and now it's starting to take a little time. And you'd like to know what happens if you have a 100,000 by 100,000 system, how long it's going to take you to solve that matrix. Okay? And it turns out that solving linear systems that are size 100,000 by 100,000 is actually quite a common thing. If you ever want to solve a partial differential equation that's a linear system, that can come up quite often. All right, and you'd like to know, is this going to take 5 minutes? Is it going to take 5 hours? Is it going to take 5 years? Right? You'd really like to know if it's going to take 5 years versus 5 hours. That might mean a big difference if you're trying to do a PhD. Okay, as my graduate students know, right? Memory, you'd like to know, can I store 100,000 data points? Okay, how much memory does it take to store whatever it is I want to do? Okay, so this is really what's the difference between, I told you at the beginning of class that all computers were the same. That a cell phone, okay, your smartphone, and the supercomputer that we used to do our research on are really, at their heart doing the same thing. But where they're not the same is in how much of their resources they have, right? So cell phone, versus a supercomputer, okay, is basically the amount of resources that they have in memory and CPU time that you're going to be allowed to use to be able to do this calculation. Okay, so let's talk about this a little bit, and we're going to start out and talk about memory. Okay, memory I think is the easier one, so we're going to start there. So basically, when you're thinking about memory, all right, you're just going to count up the number of bits you use. Count number of bits you use. All right, so this is important to know. So think about if you have an array. Let's just think about that for a minute. So suppose I have an array of 500 floats. Okay, in Python those are doubles, double precision floats. So that will be 8 bytes, which is 64 bits. Okay, this is per float, okay, per double, 8 bytes per float. So how do I find out how big that array is? Okay, I just take 8, multiply by 500, okay, and if I do that, that gives me, so I do 8 bytes per float multiplied by 500 floats, okay, and that gives me 4,000 bytes, which is equal to 4 kilobytes. Okay, and maybe just to remind you, if you haven't seen this before, all right, there are 1,000 kilobytes, or excuse me, 1,000 bytes in 1 kilobyte. There are 1,000 kilobytes in 1 gigabyte. Right? There are 1,000 gigabytes in, oh, I missed one. This is terrible. 1,000 kilobytes in a megabyte. And 1,000 megabytes. Man, some of you are probably screaming at your computer screen. In a gigabyte, okay, 1,000 gigabytes is a terabyte. Right? And I guess I'm old enough to remember when I only had this amount of memory, all right? I wasn't quite old enough to see kilobytes of memory, but I definitely remember having systems with only megabytes of memory, right? Now, you're hoping you're getting at least many of these, okay? And my hard drive has these, right? So, let's add a new page here real quick. Okay, so that's how you calculate the bytes. So if I think about a system, all right, or if a program. So if I'm let me scroll down here and just start a new page. So if I run a program, okay, the memory consumed consists of all of my my variables, okay, plus a little extra. Okay, so that little extra comes from the operating system, which needs to do things like call functions, okay, other things. Okay, there's function stacks, there's other stuff underneath the hood. I don't want to go into all that. Okay, but mostly, and for numerical computing, it's the number of variables that you have. Okay, and a lot of times, if you're doing a big calculation, okay, this can be dominated by big arrays. Okay, so imagine that you're doing some, PDE calculation a couple of years from now, and you learn you're sitting in Dr. Lignell's numerical methods class, and you learn how to break a PDE into a big system of linear equations, and you go to solve it. Well, the core memory usage of that is going to end up being the size of the matrix that you have to hold and the other size of the arrays. And so all you have to do is calculate a few calculations about what the total amount of memory is, and that'll give you the order of magnitude. It doesn't give you exactly the right number, and it turns out it's pretty easy to have your program tell you how much memory that it's using, so you can actually just have it spit out and tell you. But instead of doing that, you can, if you need to know beforehand, you can get an estimate, and you can tell, is it in this sense 4 kilobytes, and that's nothing, okay, 500 floats is nothing, or if I have 5 million floats, now I'm talking, 5 million times 8, I'm talking 40 megabytes, all right, and maybe I can't hold that many of those before I start to make, gigabytes worth of data, all right, and so, having that idea helps you know pretty quick, and you might think, well, 500, that seems like it's pretty big. But it turns out if you have a three-dimensional system, you might want something that's, 100 by 100 by 100, okay? And you can get, that's a million already right there, all right? If you have 100 by 100 by 100 in a three-dimensional system. And so arrays can get pretty big, all right? So that's memory. And so for your homework, you're going to basically have to calculate this. And my sort of promise to you is I haven't made you memorize how many bytes per different data type, and so I'll just tell you how many bytes per data type that you need to know, okay? But 4 or 8's usually, the number. They're usually almost always factors of 2, so there you go. It's not a factor of 2. Okay, so the last thing is let's talk about, and at least in this section, let's talk about running time, okay? Which is going to have to do with the CPU. All right, so the running time is determined by the number of clock cycles on your CPU. Okay, so your CPU has a clock, and it's sending data through the buses every click, 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 click. Okay, and then it's got a certain throughput of data that it can put through and a certain number of operations it can do. Okay, and so they've got all these parallel operations that they're doing: add, multiply, divide, okay, whatever. And every clock, that's why you have a gigahertz rating on your CPU. That's telling you what the clock speed is, okay, and what it's doing on the computer. All right. And if you're looking at a program, you don't exactly know in your given line of code how many clock cycles it's going to spend on that. Okay, that's dependent on lots of things, on the given CPU that you have, on the operating system, on all sorts of things. Okay, but it's going to be proportional to the number of lines that your code is executing. Okay, so while the exact time is not easy to predict, and if you want to predict it, go be a computer engineer, okay, and go learn about all the hardware and all the stuff that I don't know about, okay, and come back and teach me, all right, but number of executed, and we're going to talk what that means, executed lines of code, okay, is a good proxy. All right, and so let's look at an example to sort of see what this means, because I think it's best explained in an example. So suppose I have the following code. I have for I in range of n, okay, where n is just some number. Could be anything, okay? You know, maybe it's 10, all right? And all I'm going to do here is print I, all right? So now what's going to happen is each one of these lines of code is going to have some cost on the CPU in terms of the, so I'm going to call this line 1, by the way. I'll put out here and we'll call this line 2. Okay, so this line, it's going to take the computer some time to execute that. You know, the interpreter has to tell it, I'm going to do this. Okay, go take a for loop, increment I, the next point in the range. That's going to make some cost C1. Okay, and this print is going to take some other cost. Send this to the console. Okay, print that to the screen. That's some cost C2. All right, and then this here, the other part of the table I want to make is the number of times that this executes. Okay, so this one costs something C1. This other one costs something C2. Okay, but it runs how many times? Well, it's going to run n times. Both of those guys are going to run n times as they go through the loop. All right, and so think about what this is printing out, right? This is just going to print out, you know, 0, 1, whatever, down to n minus 1. Okay, that's, but I can write now a total time that this is going to take to calculate. That total time I'm going to call t as a function of n, because it's going to depend on what n is here. And that t is going to be c1 times n plus c2 times n. Or I can say c1 plus c2 multiplied by n. So notice that this is a linear function of n. So for loops, it's a linear function. Okay, if I didn't have any loop, it would just be a constant as a function of n. All right, and so I want, let me say this, okay? So just as the same case that we worried up here, when we're worrying about a big calculation being dominated by big arrays, okay, for the case of big calculations here, okay, they are going to be dominated by big loops. Okay, so again, think about our Gauss elimination code as a proxy for this. Think about what we did there. We had a triply nested loop. If you want to do a really big system, you're going to have to loop over the size of that system again and again and again. Okay, and so that calculation, the Gauss elimination calculation, is going to be dominated by these big loops. So if you want to know how it happens if you can run a small code and it takes a little bit of time, and then you want to get to a big code and you want to know how long that takes, what you want to know is how it changes as the size of the system changes, as n changes. Okay, so you want to know this dependence. Okay, you want to know how it depends on n. Okay, so I want to give you a quick activity to pause the video and do. Okay, I want you to see if you can figure this out. Okay, so calculate how long it takes the CPU to execute this code right here. Okay, so this is going to look maybe familiar. For I in range of n. Okay, and then tab over for j in range of n. Oh, forgot my colon here. Have a syntax error. And suppose I'm assigning an array. aij is equal to I times j. Okay, I want you to figure out, take the cost here and the number of times. Okay, and I want you to figure out for this guy, you know, figure out this table here, fill that out, and I want you to find for me t of n. What is the time as a function of n? What is that going to be? All right, pause the video, see if you can figure it out. All right. So hopefully you paused, check that out. Let's go ahead and do this together. So this is the kind of easy one. So I'm going to say this is my line 1, this is line 2, this is line 3. Okay, so how long does this one take? Well, that's C1, that's C2, that's C3, right? Each line takes some amount of time to do. I don't know exactly what it is, but it depends on the system. It depends on lots of things. All right? So now how many times do each of these execute? Well, let's think about this. I'm going to go through here, right? What's the output going to look like? Well, I'm going to go through I, and then I'm going to go through J, and then I'm going to increment I, and I'm going to go through J again, increment I, go J again. So this one is going to happen n times n times. That's a mouthful. N times n, right? Or n squared times. This one is also going to happen n squared times, but this one up here is only going to happen n times. It doesn't get repeated. So when this does 0, this goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this one goes to 1, and this goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and both of those run again. So both of these happen n squared times, this happens n times. Okay, so what is t of n? Well, it's going to be c1n plus c2 plus c3 multiplied by n squared. Okay, so now I've got something a little more complicated. Up here it was just a linear dependence for a single loop, but for a nested loop I have both linear and quadratic terms. Okay, so that leads us into our final thing, which I'm going to talk about, which is called asymptotic behavior. Let's think about asymptotic behavior. Okay, and this last part is really motivated by this question that I've sort of been dancing around, but let's just write it out fully. Okay, how can I know how long my code is going to run? Okay, run in the following case when I have a big system. Okay, and think, if you've got a little system, you don't care. It's fast, right? Everything's going to run fast. Who cares if it's a little system? It's when it gets big. So if I have, n equals 5, that's small. Okay, I don't care to predict how fast it is because it's just fast. Okay, so if I have n equals 1,000, okay, and suppose that's big, I want to know, what can I know about it? How can I relate that? So in other words, we care about when n approaches infinity. Okay, that's the asymptotic behavior. Asymptotic behavior. Okay, we want to know, what happens to our runtime as n approaches infinity. So let's think about our system we just had. So suppose I had one t1 where I said t1 of n was equal to c1 n squared. So I had something that was purely quadratic. And suppose t2 of n was equal to c2 n squared plus c3 of n. So it looks more like this case up here where I had this double nested loop. So in this case, I don't have any linear terms. This case, I have a linear term. All right? And suppose now that in my example, I have a big N. Suppose n equals 10 to the 5. All right? Now, I don't know exactly what C1, C2, and C3 are, but it's not unreasonable to assume that they're all about the same. So suppose C1 is 1.1, and C2 and C3 are about 1. Okay? So it's a little different. It takes a little bit longer to execute each one of these calculations, whereas over here it's a little bit shorter to do that. Right? So what's the time going to look like if I knew what these were? All right? So T1 is going to equal 1.1 times 10 to the 5th. Okay? And suppose this is seconds here. All right? So 1.1 times 10 to the 5th seconds. All right? Just remember 3,600 seconds is in an hour. All right? So, this is way longer than an hour. I'd have to punch it in my calculator to figure out. This is on the order of 10 to the 3, right? So this is like 100 hours. This is going to be a couple days of calculation, okay, if that was the case. Now come over here, look at T2 of n. All right, now I have 1 times 10 to the 5th okay, from this one here, plus, oh, excuse me, I totally did this wrong. This isn't 10 to the 5th. This is 1.1 times 10 to the 10th seconds. Okay, way longer than a couple days, right? Like thousands of days, right? Way big, all right? 10 to the 5th, I forgot to square it. Because now over here, this is 1 times 10 to the 10. C3 times n, that's going to be 1 times 10 to the 5th. Okay, so if I write that out, that's going to be like 1.0001 times 10 to the 5th. Okay, if I got the numbers right, because I should have, let's see, the 10th, 9th, 8th, 7th, 6th, 5th. Okay, I think I did that right. Okay, or excuse me, times 10 to the 10th. I keep wanting to write that. 10th. Whereas this one is 1.1000 times 10 to the 10th seconds. Okay, so what did we learn here? Well, what we learned is that this term, when n is big, this term doesn't matter much. So when n is big, bigger powers matter most. Okay, so think about that, what that means, right? So look at this example just again. If I had just a little bit higher of a C1, just 1.1 seconds here on this one, this is going to take 1 plus 1 times 10 to the 9th seconds. Over here, if I have this linear term, all right, instead of just the quadratic, and it takes, suppose it even takes 10 seconds to execute one of those. At 10 seconds for C3, it still doesn't come close, okay? It's only 10 to the 6th times. This one's still way, way longer to take than this one, okay? So what we can say is that we only care about the biggest power, really, all right? So we really only care about the biggest power. All right, and so we even have a notation for this. So what we say is we say that if t as a function of n is c1n squared plus c2n plus whatever, okay, with lower powers, we say that this is big O order n squared. Okay, we call that order n squared. And what we mean is that for big N, n squared only matters. Okay, that's what we mean by that. Okay, you can be more formal about this, and if you take a computer science class, you'll learn about big O and little o notation, and you can define this precisely mathematically. And I'm being kind of hand-wavy because we really don't have the time to deal with all that. Okay, I just want to sort of sketch out this idea for you to show that this matters. Okay, we could also say, suppose that I had something that was c1n cubed plus c2n squared plus whatever. Okay, this would now be order n cubed. All right, so I'll write that down. Order, oh, handwriting right now. Order n cubed. Okay, so all we really care about is the biggest power. And if you look at it, you can tell what the asymptotic order is, unless there's something funky in there like a log or whatever, right? And we're not going to be dealing with that case. So where did these come from? Where did the n squareds and the n cubes come from? Okay, these came from loops, right? When I had a loop here that was just a single loop, then I got, order n. I got something that was linear order. If I have doubly nested loop, I get something that's order n squared. So let's connect that back to Gauss elimination for a minute, right? In Gauss elimination, right, I had forward elimination. Forward elimination had a triply nested loop, so that's order n cubed. Back substitution had a double nested loop, so it's order n squared. So think about that. Which of those is going to cost more when I have a big system? Is it going to matter more that I'm trying to do forward elimination, or is it going to matter more that I'm doing back substitution? Which is it? That's right, it's forward elimination, right? Forward elimination, if I had n equals 10 to the 3, right, this one is going to give me 10 to the 9th, and this one's only going to give me 10 to the 6th. So even if each one of these calculations here is faster, there's no way it's 1,000 times faster to execute all those lines. And it wasn't, right? The forward elimination was a little bit longer, and the number of things you had to do in the multiplications. So it dominates the calculation. So overall, the Gauss elimination calculation, if we say what is Gauss elimination, it is order n cubed. Because if I had an n cubed terms, n squared terms, whatever, overall Gauss elimination is like an n cubed calculation. Okay? And you're going to do an example on your homework where you're going to see that the cost, the time it takes to run on your computer, goes up like the cube of the size of the matrix. Okay? You're going to do this on your homework. All right? To show that this is the case. All right? So I want to do one more example to show how this can be practical, to actually do these calculations. So how is this practical? Okay, and one of the reasons I teach this is because this is something that happens all the time. Okay, I do calculations all day long, and we do this all the time. We calculate the size of our arrays and our matrices to predict how much memory we're going to use, and we predict based on asymptotic order if we run bigger calculations what's going to happen. Okay, we do this in our head even. This isn't a calculation we do all the time. So suppose that I am doing a calculation. Suppose it's just back substitution. Okay, just back substitution. So I know that my time is order n squared. Okay, that means that I can say that the time is approximately some constant times n squared. That's going to be the dominant term. Okay, I can put an approximate there. Sometimes if I put equal sign there, people start to get a little squirrely. All right, but we're playing a little fast and loose with algebra because we're taking n to be big. All right. Now suppose that I can do a calculation on my computer. So suppose I did a calculation on my computer at n equals 10 squared. Okay. And I found that t of n is equal to 10 seconds. Okay. So I had a 100 by 100 matrix. Maybe I made it up. Maybe it was part of my homework. Okay. I did the back substitution calculation. I found out it was 10 seconds. Okay. The question is, how long will it take for n equals 10 to the 4th? So this was 100. Now I want to go up to 10,000. How long is it going to take? I want you to pause and see if you can figure this out. Okay? See if you can do it without me telling you how to solve this answer. It's not that hard to do. There's a trick to it, okay, just to see. If you see it, maybe you'll be able to do it real quick, and then you'll remember better if you try it anyway before I tell you the answer. Okay? So hopefully you tried it. Okay? Trying stuff before you know the answer is a great pedagogical technique. All right? I don't know if I'm really helping encourage you to do this in the video or not, but it's a thing as a student. It's a hack you should learn. Okay? Because if you try it first before you know, there's something about it that primes your brain to get the answer. Okay? So there's a couple different ways I can do this, but the way that I think are the most straightforward is I can just take and equate these guys when I know that n is 10 to the 2. So I can say 10 seconds is equal to c times n, which is 10 to the 2 squared. Okay, and now I can solve for c. So c is now going to equal 10 seconds divided by 10 to the 4th, which means it's this time constant, which is 10 to the minus 3 seconds. Okay, so that told me that, on average, right, my c, my constant of everything is happening is 10 to the minus 3 seconds, right? Now this one, like I said, this depends on everything. Is this a Mac? Okay, is this a PC? Is this, what processor? Intel, is it an i7, an i5? What is it, right? All that stuff is going to go into what that number is, right? What interpreter? Is it compiled code? Is this C++? Is this Python? Okay, all that stuff is going to go into determining that number, right? So that you're just going to measure, right? You're going to do this calculation. This right here, this thing you did an experiment. You measured, okay, by doing that calculation. But now you want to do your prediction. You want to say what happens when n is 10 to the 4. Well, now you have your constant right there. You know it's 10 to the minus 3. So now you just need to evaluate at 10 to the 4 what you have. Well, it's c times 10 to the 4 squared, which is c times 10 to the 8. Okay? Well, we know c, that's 10 to the minus 3 seconds, times 10 to the 8. And what does that give us? That gives us 10 to the 5 seconds. Okay? So there, 10 to the 5, like I said earlier, 10 to the 5, if I know that 3600 seconds equals 1 hour, if I take 10 to the 5, this is approximately, right, 10 to the 3, if I really round down. So this is, and this is going to be on the order then of 100 divided by 3. This is going to be about, what, 30 hours? Something like that. So this is going to be like a day. Okay? So I went here from 10 seconds at 100 to a day at 10 to the 4. Think about that. Okay? Now notice what's happening here. All right? Notice that the time is going up quadratically. So if I'm going up by 100 times, okay? So I had 10, this is the other way to think about it. Okay, if I had 10 seconds, all right, I went up by 100x, okay, in this, in the size of the system. But it's squared, okay? So now this is 10 seconds, 100 times, this is now 10 to the 2 squared. This is also 10 to the 5 seconds. Okay, so this is the alternate way of thinking about it. Maybe I said that quickly, but this is the way you can do it in your head after you've been doing it for a while. As you look at this and you said, well, I'm going to make 100 times more calculations, right? Here, what you're doing here is taking a ratio of 10 to the 4 divided by 10 to the 2. So this is the new one, okay, and that is the old one, okay? And then you say, what's the order? Okay, you take the power in the order in the numerator, or excuse me, in the exponent. So you say 10 to the 4 over 10 to the 2, that's 100x squared. That's going to be my multiplier. Okay, so that's my multiplier. All right, and in that case, 10 to the 2 squared is equal to 10 to the 4. And now I multiply that by my time constant, or by my measurement, which is 10 seconds. Okay, that's my measured time right there, and that gives me 10 to the 5 seconds as well. All right, so if you see something, and you might think that everything's linear. That's kind of the way our brains are trained to think, right? So you might think that if the calculation was 100 times bigger, that it would take 100 times longer. But it doesn't take 100 times longer. It takes 100 squared times longer. It takes 10,000 times longer. Okay, so here, right, when I went from this to this, I might have thought, well, it's just 100 times 10, so it'll take 1,000 seconds. 1,000 seconds is like a quarter of an hour, a third of an hour. All right, so but this is going to take an entire day. It takes 10,000 times as long because it's squared. Okay, so you can see how it is that the loops are what dominate the calculation. If I have a triply nested loop, then it would be cubed, right? And 100 cubed, is yet what? 100 times 10,000, which is what, a million? Okay, that would be 1,000,000 times longer, right? Now you're not talking a day, you're talking 100 days, right? You're talking a third of a year, or a quarter of a year. Okay, so let's just step back and review where we were in this video, what we talked about. All right, covered a lot of ground, so let's kind of recap where we're at. So we started out talking about Numpy linear algebra. We said these are ways to do the same things we've been doing in Gauss elimination, all right, and in the loops and in the sort of 3 or 4 days that we've been doing over the past couple days. And we've been building and building and making you do this work, and now I said, we've done enough, now you can have the easy way of doing it, all right? So now you know a little bit how it works. Now go ahead and use the easy Python functions to do it, okay? So that's what we did first. Then we said, now that we understand a little bit about how this stuff's happening under the hood, we understand arrays, we understand this stuff, let's talk a little bit about how much memory and how much CPU time we're going to consume when we do these calculations, all right? So what are our algorithms going to do if we go from small to big? And so we said, let's talk a little bit about memory, which you can calculate by just taking your biggest variables in the system, your arrays, and multiplying them by how many bytes each that data type takes up, summing them up, and that's what you get. That gives you a pretty good estimate. For the CPU time, it's a little more complicated. You need to look at each line of your code, okay? and think each time that line executes, that's one more amount of computation time that it takes. But it turns out you don't really need to pay attention to every single line in your code. You need to pay attention to lines that are executed n times by whatever scales your system size. So in gas elimination, it's those nested loops. Okay, and it turns out that each loop gives you a factor of n. And we talked about asymptotic time, and we said as n gets really big, we only really care about the big powers. So here we only care about the squared and not the linear power. And if we were to do it with a cubed, we'd only care about that one. And what we showed is that we can say that we call that asymptotic order, all right? And we only really care about that. That's how we show it, is we say that it's order n or squared or order n cubed or other things, n log n, okay? There are calculations like that, all right? And then we showed that a practical way that you can use to take, if I know my calculation takes 1 minute, and I have order n, I can tell you if I have a bigger system, is it going to take 2 minutes or 10 minutes or 3 days? All right. So that's what I have to tell you about Numpy linear algebra and about computational cost. And I hope you have a great one.